Hello, and welcome to my talk on applications for machine learning in IoT. The topic of my discussion today really about applications in IoT. I'm going to talk a little bit about this from a practitioner's perspective. So the key things that we should cover today are, what are the elements of an IoT deployment? What do you need to think about when you make deployments to enterprises? If you have a startup and you're looking to scale it up, what are some elements that would make you more successful than otherwise? Your deployments need to be secure, they need to be reliable, and they need to have a number of valuable partnerships that can right away add concrete ingredients or assets that can make your problem statement solution much more successful. So our team at Intel, and I manage a program for ISV enabling, really focuses on vendors and how we can help them build their solutions on Intel IoT platform. We do this by helping them with rapid prototyping, early proof of concept engagements with customers, and essentially bringing in learnings that can have potential impact on the investment. There are a couple of key elements to really keep this in mind. One is, what's the time to, and the second is the go-to-market approach. Working with Intel, there are a number of things that you can certainly utilize in terms of security and also in terms of cloud manageability of these devices. Having 1 or 2 or 5 or 10 devices is not a big deal, but if you're deploying in the thousands, it's essential that you have very secure way of communicating updates and also reliably extracting data from the devices and pushing it to the cloud as and when necessary. So a part of my presentation today will also focus on forecasting. I'll provide a short tutorial on time series data analysis. This is a question I get most often, which is how do you basically extract insights from data that is not quite your general machine learning type of data. It's a classification problem if you're looking at failure. But when the input streams are time-based input streams, when you have multiple input streams coming in, how do you try to make an evaluation of some predictive model? How do you get your classification done? What are some of the graphical tools that you can utilize in this area? So we'll look at forecasting. This is a very important element of any insights-based IoT project. If you are a startup that's developing solutions, learn about how to work with Intel through the program I manage here, and working with some amazing people, both on the engineering and the business development side. One of the things that I want to also try and cover given time is a little bit about neural networks and of neural network that can help you bring in deeper insights. Recurrent neural networks are one of the most used tools right now in doing time series analysis. So we'll talk about that. So I just talked about all of this. You know this. Why do we really bother about IoT at the edge? There's a lot of excitement around IoT. That's why you're probably here. Listen to some of these presenters talk about the impact of IoT in the real world. The networks that essentially connect small devices, make them smarter, make our decision making smarter, is getting more and more ubiquitous as time goes along. And we also have economies of scale in terms of sensors, compute, and storage that allows us to build very cost-efficient deployments. One of the key things that folks really don't know about is that 85% of the devices that are out there are not actually connected, right? So that's the data on the slide. And what you really find is that the cost of sensors has been down, the cost of bandwidth has been down, and the cost of compute has been down, right? So this creates an opportunity, in fact, and I believe we're at an inflection point to take words from a very smart person at Intel who happens to be the CEO, connect the unconnected, and proliferate computing across the compute spectrum. A quick background on me, about me. So I come into this role with some work in sensors at National Instruments and also at IBM. I went out and got my PhD in statistical optics and patterning technologies in a little known area called optical lithography. And one of my earlier product development work was on MEMS, micromirror-based imaging models. Been through a variety of roles at Intel. It's been an amazing journey. And through this process, and also through my earlier career, had about 30 publications, some patents, and then I took a swing on the software development side, and that's where I am right now. We have an amazing team that helps with the enabling of ISVs in terms of helping them get their assets built up on Intel platform. I really like this quote, right, which essentially says that, computers, back in 1966, right, if you know of Steinbach, he was a pioneer of his time. And I think this quote is just now coming to reality. In fact, we are right at the tipping point of computing being very ubiquitous. So a quick word about software enabling. When we take a look at partners around the world that can help in building reliable IoT solutions, it's very important to understand that the size and scope, while it's really, really massive, it's also important to build out really good partnerships, because it's unlikely that in a very fragmented IoT world, you're going to be able to take care of the entire solution on your own. You'll need aggregators, you'll need solution system integrators, you'll need ODMs, you'll need other software partners. If you have an analytics engine, perhaps you need a database. If you have the hardware that has very powerful compute capabilities, you probably need sensors at the edge. To motivate that, I'm going to show you this one slide that I put together to really, have sort of a one-sided, multifaceted view of what are some of the ingredients that go into an end-to-end IoT stack. So think of this as a reference architecture. Underlying the reference architecture, you have your hardware devices, such as your Dell, Cisco, Eurotex, and they're connected to any number of sensors or actuators, right? Pulling in data from industrial equipment, and you may even have some ARM devices at the end, right? So all of that works okay. Sitting on top of the gateway, you can have a number of IoT platforms, and these are essentially IDPs. We have had ThingWorks, Pulsar, Exosite, Honeywell. So in the building management space, in the retail space, in construction, what have you, these platforms allow applications to run on top of them. The likes of Circle and Machine Shop or Solus or InfoSwift, these are some partners that have really provided very strong middleware components in terms of analysis, messaging, database, etc. So far, you really have the story of the edge, right? But somehow, in some way, you need to communicate this in very different environments to the cloud as well. And that's where things like the cloud service providers come in. And when these solutions are deployed to the cloud, you want to do it reliably and securely. So Intel EPID is a solution that I'll talk a little bit about later if I have time. Sigfox and LoRa, these are low-power wide area networks. You have Helix Device Cloud and things like Amazon IoT. There's an Azure IoT offering as well. And then sitting in the cloud, there are a number of offerings from SAP, Oracle for building data lakes. There are open source solutions. And so this is where your data eventually ends up, at least some amount of data that can help you do reliable training of your of your inside of your sensor data. There's an application matrix that I've really put together with a number of offerings that come in from different providers. So jumping on, so the lack of IoT standards will definitely slow us down, and Intel is a huge part of the Industrial Internet Consortium, OpenFog, and Open Compute platforms. And without the help of these industry partners, it's really hard to tackle something that's really complex as IoT. So let me now walk you quickly through some of the domains that are disrupted by IoT and machine learning. And I'll try to motivate it with a few specific examples. The area that our team really works on over here is squarely around industrial manufacturing, transportation, smart building, energy, utilities, retail. So if I take a look at industrial manufacturing, currently this area has a component stack that's around machine-to-machine communications. So imagine you have an equipment that's building, I don't know, an ultrasonic welding machine, or it's creating some gadget, and it needs to have the right temperature and voltage parameters in order to work efficiently. It's very hard for folks to real-time have that level of insight from the sensors that are streaming data live. And so machine-to-machine communication enables these equipment to run very efficiently and helps in predictive analytics. So I'll talk a little bit more about that in more detail in an upcoming foil. Likewise, with healthcare, you have issues around patient tracking, asset tracking. Authentication is a really big deal, obviously because of privacy and other issues. In transportation, you have machine-to-machine communication again, vehicle-to-vehicle communication, ADAS, and essentially an awareness of the environment. So the challenge here continues to be how to optimize delivery, as the average floor-loaded trailer could carry a lot more cargo, for instance, right? If you were to know what the failure mechanisms are. And then you have retail and smart living use cases as well, which I'll try to cover in a second. Okay, so let's actually take a look at smart manufacturing in more detail. So in today's on-demand world, consumers expect shorter delivery times, and they challenge manufacturers to find more efficient ways to fulfill orders. So with the visibility of mobile and IoT solutions, the warehouses can start to provide flawless on-time fulfillment, right? So you have cost savings that come in, and here you have machine-to-machine communication. For instance, there's a sensor that detects ambient light is going up or down, and likewise you can turn the light bulb down or off or on. You can have cost savings, right? And now you need to have some visualization around that. So instead of having regular cadence preventive maintenance, such as every 2 months have somebody come in and take a look at the equipment, now you really are looking at predictive maintenance. So you want to get the equipment running for as long as possible. And if you need to reduce the output by, say, 20%, but you can get the equipment running for another 2 weeks, then that's perhaps a better decision to make. There's also the question around flow optimization, right? How do you basically get the right routing for the manufacturing process so you can take advantage of a machine that needs to undergo maintenance versus not using using a machine that doesn't. And then finally, there's very complex real-time dashboards. There's a tool that's called Grafana. I'd love if you guys want to check that out. It is really amazing in terms of the capabilities it provides, with sensor feeds coming in from any number of real-time databases. So what about something like enhanced patient care? So it's no secret that the US healthcare industry is overpriced, it's inefficient,
There was a study in, I believe, 2012, where the authors reported that the US was spending around $2.6 trillion on healthcare every year. So, and 600 billion of these costs, really are about treatment that either do not help or, actually cause harm. So the idea around healthcare really is to have the payers and providers set up the infrastructure, and the target is to lower the readmission cost. And this is one of the, if you talk to anybody in the healthcare industry who's on the operations side and also on the medical side, they will say that readmission costs are really high. So from a patient perspective, also from the hospital perspective, it becomes really important. So patient tracking for IoT is significant. Around asset tracking, oftentimes, patients that don't have a wheelchair, they can be escorted out of the hospital. So it's really important to track something as simple as, where is a wheelchair? And there are cases where lack of availability of wheelchairs can actually result in a patient staying overnight if the time is passed during the day for them to check out. Then you have access control, right? Streaming protocols. And finally, when you do all the data aggregation, it needs to be HIPAA compliant, etc. So I have a reference over here. When I publish the PDF, you'll be able to take a look at this in more detail. The next larger topic really is around smart buildings and smart cities, right? And again, you're bringing in energy efficiencies, and you are essentially looking at temporal space utilization. So here's a building map or a floor map of an office building, right? And when the planning is done, it's not exactly clear how well this area is going to be used. But by putting in sensors, either with the lights, that are in the light outlets, or putting in sensors that can measure or figure out the presence or absence of people, it becomes really useful to understand what is the flow of the workers. And finally, you have things around water savings and maintenance. Also, one other quick point that I want to make is that these things are not supposed to be very complicated, right? The solutions that are built up now come with some very efficient and high-level programmatic tools, essentially visual tools, that allow a facilities operator or a planning person to actually try to figure out, okay, what is the, they can actually do their own analytics. In this slide, I really want to talk about essentially a high-level platform architecture. So there are two major IoT challenges that are, in connecting the legacy devices to the internet, and then ensuring that all the IoT and machine-to-machine communication is seamless and secure. So the Intel IoT gateways serve machine-to-machine and mobile environments, and they essentially interoperate with any messaging appliance. So in this case, I have a data agent at the edge that goes to a database on the cloud. You have cloud data ingestion software. You have an enterprise service bus. You have cloud analytics software. You have a database at the gateway itself. You have service orchestration, so on and so forth, right? So serving up all of these applications in the cloud, you have an edge analytics agent, which again has its own database, manageability, security, and sensor middleware. So take a look at Intel's IDZ platform, Intel Developer Zone platform on softwareintel.com, and you'll actually find really amazing resources in terms of how to bring in ubiquitous connectivity with over 300 sensors, industrial-grade sensors. So I'm going to talk a little bit around time series data analysis. As I mentioned earlier, one of the bigger questions that keeps coming back is really around, what is the necessity, what is the importance of latency, and how do you really get insights around this? So let's motivate that a little bit, right? When you deploy IoT applications, say you're monitoring a car that's speeding ahead on a freeway, or if you're looking at a machine that's churning out gadgets at 10 a minute, and there's a certain cost to having a downtime, either a personnel cost, safety issues in case of automobiles, or there's issues around worker productivity or equipment productivity. What you really need is real-time and low latency reaction. So as the data is streaming in, whether it's voltage, humidity, sensor data around temperatures, you need some level of edge computing to figure this out. Sending all this data to the cloud is problematic from two different perspectives. One is simply the latency that's engendered in sending all the data to the cloud for any sort of machine learning. Oftentimes, if the latency is more than a millisecond or so, then it's too long for real-time decision-making to happen at the edge. The second really is also around cost concerns, right? When you're generating terabytes of information across all these data, and 99% of it is effectively not failure related, you are sending in, or 99% is essentially not action oriented. You're sending a lot of unnecessary data to the cloud. So you want to try and build out an edge environment that does this in a cost-effective manner. So there's basically three criteria when you're trying to do time series analysis. One is you should have a constant mean, right? So mean should not be changing as a function of time. For instance, in this time series, you're basically taking this data and it's moving, there is an upward trend. So the second one is really around homoscedasticity. Homoscedasticity is really, if you take the variance of this data, and if that changes over time, so if you take a look at this, it's not uniform at all. And then you have constant covariance, which is essentially the spread of the graph changing up or down. So the way to tackle both of these, three of these issues is really around differencing. And I'll talk about that in just a second, of how you can bring in the mean and how you can actually remove the variance in your data, or have constant variance, sorry. You're always going to have some variance. Here's an example. I actually just created this graph on my own, but it's indicative of a time dependence, Gaussian variation. There's some normal parameter that's creating this, but there's also a time dependence of the mean, right? So here you have a mean that's kind of flowing down, and on the right-hand side, you have a corrected version of this. So in a real-life example, you can think of this as the Dow Jones Industrial Average. If you take a look at it through the entire day, you're going to find that, okay, it has some trend going down, or in recent years, it has a trend going up. That type of data is hard to use, and you need to find some way of normalizing it. So what you do is provide differentiation, and this is essentially an example of just that. So if you take a look at any daily averages of Dow Jones Industrial Average, then you'll find out that it's much more uniform in mean. Okay, but so as with the previous example, the time series data is not domain specific, right? It's financial, it's market related. You have customer churn, CTR, all that, and then of course genomics. So in our case, when we take a look at predicting the future from the past, that's really the main task of data scientists in IoT. The specific use cases, often talked about building temperature sensors all over the room, and when should we turn the AC on or not. So let's say you're finding out that the temperature outside is dropping rapidly, right? And there's a certain lag in terms of that coming into the building, right? So by the time you turn the AC on and you cool the building, you're going to find that the outside temperature has already dropped. So there are ways in which you can essentially minimize this. The second is really around time series anomaly detection. So forecasting pattern, the same pattern, forecasting around anomalous behavior is very interesting as well. It's very easy for our eyes to kind of pick out generally what the failure points might be, but oftentimes you need algorithms that are trained in forecasting behavior. One of the better models that's come along in recent years is autoregressive moving average model. I won't go into a lot of detail around this, but what you really see over here is some sort of seasonal data that's coming in, right? So months of June, July have high peaks pretty much every year. So you need to identify those. Now, if you had that high peak at a different time, say in January, then you need to identify that as well. So in regression, you have a dependent variable y and a dependent, you have an independent variable y, x, and a dependent variable y, and you're essentially regressing y on x. And as you measure the epsilon, you're able to figure out, how good your model is. So in time series, you can essentially regress on time t1 to time t0, and that's auto-regression, right? So you have data that essentially looks at just the previous timestamp of itself, add some systematic error terms, and then you get your current model. Again, when I publish the PDF around this, you'll be able to see the workflow. There's some really good repository from UCI that you should probably take a look at. There are a couple of items that I want to talk about quickly in terms of what Intel software tools are available. These are really geared towards cloud compute, but you can certainly create a model and deploy it to the edge. One of the things I forgot to talk about earlier in my architecture slide is that you create a model such as predictive maintenance markup language based compatible model. And so while your code can be running in something like R or Python, at the edge of the network, you can actually deploy it with very low level compute because the model then translates from the cloud to the edge. So one of the things that I was going to talk about today was also with machine learning. But before I go into that, let me actually take a quick peek into the chat side. Looks like there's no major questions here. Okay. So this idea really started off in the 1950s with Arthur Samuel, right? And he liked to play checkers, so he wrote a computer program that he could play against, right? So he played, he won, he played, he won. But finally, as the computer learned more and more of his steps, it started to get a little bit better. And this entire thing was basically developed as a decision tree algorithm. If you have heard about Google's AlphaGo program, it more recently actually started learning on its own, right? So as the computer, as the algorithm played against itself, it got smarter and smarter. Here's another quote that I really like. So learning without being explicitly programmed. In very recent years, right, in 2012, a massive breakthrough occurred in machine learning. Back in the 1980s, George Hinton did really good work on perceptrons. Until then, it was really thought that these neurons, while they sort of had this facsimile of mimicking the human brain, they didn't really have the compute capability at the time to realize the power of a neural network. And one really critical element was missing that George Hinton's work on perceptrons solved. And he realized that as you have input units, that are going out and taking input from an image, or even in our case, time series data, and that value propagates through some hidden nodes, and it makes a false detection, for instance. What he realizes is that you need some backpropagation method, right, that will essentially take that and change the weights of the neurons in the intermediate hidden layers. And that backpropagation method was really, really important in making neural networks successful. So if you have time and inclination for this, I would highly encourage taking a look at the 2012 paper that talked about classification with convolutional neural networks, right? And This was basically seminal in the fact that it beat out all other algorithms in terms of object recognition in images. And this was all done as a result of using backpropagation and a really deep neural network. I think they used something like 12 layers. When you take a look at artificial neural networks, right, what you essentially have is an input set of neurons that that take in data. So imagine the data is a single pixel from an image, or let's say the data is time series, temperature measurements, and another, voltage measurements, so on and so forth. And they generate a value, right, that's essentially a weighted sum of their inputs times the weight, right? And you have a function that allows the output that's coming from any one of these neurons that's capped between two bounds. So usually sigmoid or hyperbolic tangent functions are used to get values between -1 or 1 or between 0 and 1. And so what you really find is that the initial layers, try to figure out overall edges, and then they try to figure out corners and shapes, and finally you have object recognition. So you probably remember this from a few slides ago. This is our time series model that's showing the data, moving in a downward fashion. So this could be your voltage signal, and then this is your normalized voltage signal. So in order to train something like this in the cloud, the reason we are doing all this is really because of product line failure detection that we want to undertake, right? So one of the areas that we work on very deeply in this group also is around training of the sample data. So by sending in select 10% of the data to the cloud, you're able to train the algorithm, and 70% of the training set actually is used. Then once it goes to the cloud, 70% of it is used for training, and then the remaining 30% is used for prediction. So there are a number of mechanisms by which you can actually do this regression, classification, and clustering. Some of this is supervised learning, and the other is unsupervised learning. This is an example of linear regression and the example of logistical regression, right? So this is a sigmoid function that I mentioned earlier that caps the output of the neurons between 0 and 1. Okay, so moving into deep learning, I mentioned this earlier by the motivating examples around neural networks. Here I have a very simple flowchart of how you can, essentially build your own neural network. So let's say you have 3 parameters around age, employment, and income, and so these are your features. And the output you're trying to figure out is whether the person is married or single. So your input layer has 3 streams of data, and then you can have a hidden layer, you can have a second hidden layer, and you made a choice on the activation function, like the sigmoid function I mentioned earlier. The age vectors then come in, and that value is passed on to all the hidden neurons. In one version, this is basically a topology. In one topological version of this, you're passing this value to all the hidden neurons. Along with this, every edge connecting any one layer to another layer, any one node to another node, there's a weight associated with that. So what you basically do is do a weighted average for the input and the edge weight to get the value of a neuron over here. So this basically becomes a dot product of the weights and the input terms. You carry this forward, and again, this is a dot product of the previous layer and the weights connecting in. And finally, you get your output layer, right? So you could have any number of layers in between. Of course, the computational complexity gets deeper the more layers you have. You have to make a choice in the number of nodes in each layer, etc. And this is where a lot of different compute topologies actually come into place. You have CNN, you have recurrent neural networks, etc. So what I'm going to talk about here really is around recurrent neural network-based forecasting. So here you have connections between neurons that form a directed cycle. So take a look at this example. In earlier incarnations of neural networks, you essentially had the flow of data going through on one side. Hinton came along and said, you know what, this is probably not right. You need to propagate the errors back over here and update the weights, right? And as it goes through different epochs, it actually gets smarter and smarter and is able to make better predictions, knowing where it has failed. The recurrent neural network version of this is really a little bit simple, a little bit more complicated, actually, not quite simple. So you have connections between neurons, right, that form a directed cycle. And with this feedback mechanism, you essentially have this quote-unquote time dimension that brings in memory into the neuron. So let's say that your current value, if you're measuring equipment, if you're measuring a pedometer or whatever else, is dependent on the last 2 or 3 measurements itself. So this type of topology in neural networks actually starts to learn the context. Okay, so I have a lot more data around this, but I'm running a little bit out of time. So I'm going to quickly jump into some of the technologies and platform that our group uses in order to help the software vendors get better deployments in the cloud. So essentially, when we take a look at this, we have something around secure device onboarding. So today, a lot of customers are actually struggling with deployments to the cloud, and these deployments are challenging because the data is potentially not secure. You can add devices, you can remove devices, and that's the reason why it becomes a little bit difficult to a facilities manager or a health service provider to automate with IoT platforms. That's a reason why Intel recently announced secure device onboarding. If you're looking to get started, there are a number of hardware platforms that Intel works with that now come in with a number of applications from several of our partners as well. So you can take a look at this portfolio of partners. We also have several resources on intel.com/IoT. So take a look at that and let me know if you have any questions. You can always reach out to me at my LinkedIn, and also through, I think I provided my, I'll write it here as well, and LinkedIn is the same username. I really wanted to talk, in a little bit more detail about this, sort of trying to manage my time a little bit better also. So one of the questions that always keeps coming up, right, is really the idea around how do you transfer edge data, how do you do analytics in the middle platform, and how do you get the training done? So by leveraging, existing sensor platform, sensor partners, utilizing some microcontroller unit that works directly with these sensors. Sometimes the sensors are able to communicate directly with the gateway. What you essentially do is run a series of containers or applications that are secure on the gateway itself. So when you're taking a look at industrial IoT, you have database or manageability solutions all running in parallel at the gateway, taking in this stream of data. Usually the data transfer happens in terms of specific message protocols such as MQTT. And there are tools like Mosquito, RabbitMQ that allow you to look at that incoming stream of data and then send it to the cloud, where you can So you selectively send this to the cloud. So that's the 10% of the data that generally can go to the cloud, and you can start building your applications by training on that data. When it comes to the cloud, you can run a number of business logic rules, right? That's the outcome of the training. You can deploy the rules at the edge as well if you need to take some real-time decision making. But how do you really do that? So one of the ways to essentially do that is by having a PMML model. Oftentimes, the cloud services run in tools like, in languages like Java or R, which may not be easily transferable to the edge. So you deploy the entire training model or the trained model in the form of predictive machine markup language, and get it running with very low compute cost at the edge. Some of the tools that are used very effectively in the cloud, I mentioned Grafana, InfluxDB, Akka, and Kafka. These are all tools that work in and around data lakes, provide visualization and other things. So I think with that, I'll probably end the presentation. I know we have a little bit of break over here, but again, get back to me if you have any questions, and I'll be happy to answer offline. Thanks a lot again. Bye-bye.